Okay, we're back here. It's Wednesday. We're going to go on chapter 28 to the second part of our discussion of circuits, DC circuits. We started off yesterday with a little bit of an introduction to what a DC circuit is, wiring diagrams, and applying Ohm's law, Kirchhoff's voltage law, and current law to solve a couple problems with a single resistor. We're going to get on to slightly more complicated circuits today. But first, we're going to go into a couple other topics briefly. First of all, you're making all these calculations of current and you're studying circuits, but we need to go into a little bit of the physiological impacts of current so you can appreciate the dangers of not using proper safety protocols when working on your circuits. We're going to get into an analogy between electrical and water circuits, how to calculate energy and power, which as a consumer is of importance to you. And then we're going to get on to series and parallel combinations of resistors in short and open circuits. We're not going to be able to finish this all today. We'll finish up what we don't tomorrow, and then I'm anticipating we'll finish up chapter 28 on Monday. There will be a homework 10 on this chapter. I have the tentative due date of Sunday the 11th at 11:59 p.m. It will not be pushed up any earlier, but I could possibly delay it a day or so. Let's just see how this goes first. Here are the learning objectives as always. So you're performing all these calculations with circuits, and we're studying current and voltage and resistors, but it really doesn't mean much unless you have an appreciation as to what's a large current or what's a damaging current. So I'd like to just spend a minute to go over this. Most of the circuits that you are dealing with in the lab, well, virtually this year, are dealing with currents, have currents on the order of a couple milliamps or less. So what happens there? Okay, this is enough current that if you short circuit through you, or if you touch the wire, both ends, you can get a little bit of a tingling from. You're not going to die from it, or any serious problems, but it's enough that you need to be careful, right? A couple milliamps is enough to give you a little bit of a shock. You start getting up, to the tens of milliamps. And you see this depends a little bit on gender, and it depends a little bit on the frequency if this is AC. So AC current coming into your house is at 60 hertz, 60 cycles per second. It depends a little bit on that. But when you start getting into the tens of milliamps, you can get a shock from this. And in some cases, your muscles contract and you lose the ability to let go of the wire. And so this is obviously bad. You start getting in, around 100 milliamps or so, 50 to 150. Now it's potentially lethal. And definitely when you start getting up to a half of amp to, a few amps, there's death is likely. And this is important because these are the types of currents that can be supplied by the circuits in your house. Okay, so it's always important to turn the circuit breaker off before doing any wiring on your home. If you're putting in a ceiling fan or you're putting in a dimmer or something, turn the breaker off because this is enough current to kill you. So I just wanted to bring this slide up not as the bearer of bad news, but just so you know roughly what some of these currents mean. Like what's a big current? What's a small current, okay? Something of a milliamp or less, you're pretty safe. Not that you shouldn't use precautions, but when you start getting into household wiring or some of the circuits, for some of your powered electronics at home, your yard electronics. You have to be careful. This can be lethal. So these are just just keep this table in mind. The second thing I want to do before we get into too much detail is I want to really continue to make the analogy between water circuits and electronic circuits. And the reason I'm doing this is most of you have a little more experience with the plumbing in your home than you do with electric circuits. And it's easier to visualize water moving through pipes sometimes than it is charge moving through wires. So there's a lot of analogies we can make between water circuits, closed loop water systems in your home, and electrical circuits. The easiest one to make is that they both form a closed path for something to flow. Okay? In a water circuit, you have pipes, and these pipes form a closed path, and water flows through the path, or paths if you have different T's and different circuits. Electrical circuits are the same way. Okay, you have charge flowing through wires, and this is a closed loop, a series circuit, but we could have more complicated circuits too. And so water flows through pipes, charge flows through wires. In both cases, you need some source of energy. Because water flows downhill, right? So we need a pump to pump water uphill against the gradient. Similarly, charge flows downhill, right? Positives and negatives they don't want to be separated. And so we need a battery or some energy source to do work to separate the charge to get a current, okay? So no battery, no current, no pump, no flow. So these are the sources of energy. Pump, battery. Water flows through pipes, charge flows through wires. Okay. Here you've got a receptacle. Okay. There might be voltage behind it, but there's no current if nothing is plugged in, right? So by Ohm's law, the resistance is infinity if nothing is plugged in here. Okay, you don't use any electricity if nothing is plugged in. Similarly, we could go here and you have a faucet. So a faucet has pressure, right? Pressure plays the role of voltage. Faucet, if it's closed, has pressure, but you don't get water flow until you open it. In other words, the resistance to water flow is infinity for a closed faucet, just like the resistance to current is infinity if nothing is plugged in. Okay, so there's another analogy. Then you have pipes for water circuits, and you have wires for electrical circuits. Okay, so when connected across a potential difference, if you connect a wire across a potential difference, you get current flowing through the or electrical circuit with little resistance. And if you connect pipes across a pressure difference, you will get water flow with little resistance to flow. So again, pipes, wires. Okay. Now we have, remember, resistance of the wire depends on the diameter of the wire, and it depends on how long the wire is in the material, right? And so remember that the resistance increases with the length of the wire, and the resistance is less if we have a larger diameter. Same with pipes and water flow. The resistance to water flow, if you have a given pressure difference, is greater through a longer pipe than a shorter pipe, and the resistance to water flow is greater if there's a smaller diameter than a larger diameter. Okay, so current, water flow, wire, pipe. And so we're going to continue to make these analogies just because I think it's more intuitive, at least for me it is, and for many first-year students as well. It's more intuitive to think of this water flow than it is what's going on in an electrical circuit. You have a junction rule. We have Kirchhoff's current law, which states that, remember, the current into a junction equals current out. Okay, well, here, if you have water coming into a T-connector breaks the water flow off into two different paths. Whatever water comes in must come out. So the same laws apply in different forms to water circuits. So we're going to continue to make these analogies. The next topic I want to get into is relating current and potential difference to energy and power in the circuit. So back in chapter 25, recall that if you have a charge Q and the charge moves across a potential difference, delta V, it will gain or lose potential energy, right, depending on the sign of delta V and the sign of Q, right? And the change in the potential energy is delta V, which is the potential energy change per charge times the charge Q. Okay, and this, for example, is a charge Q, for example, being pushed from the negative terminal toward the positive terminal. Okay, what we want to calculate in this chapter is power, or the rate at which energy is transferred, and power is energy per time. So let's, for example, calculate the rate or the power that a battery or any source transfers energy to the charges as they move through the battery. So to calculate power is delta U over delta T, change in energy over the change in time. And we plug in delta U is Q delta V. And if delta V is constant, right, we're pushing charge over to the other plate, then this becomes delta Q over delta T times the battery voltage. And this is just equal, delta Q over delta T is the current. And so we get that the power generated by the battery is equal to the current supplied by the battery times the potential difference across the battery terminals. So if this is 9 volts for a fresh 9-volt battery, we multiply that by the current, and that's equal to the power generated. Now, one important note that the author makes: when you buy a battery, that battery is meant to provide a constant voltage, 9 volts, until the electrolytic paste starts to get used up and the battery ages. So this is fixed. The current depends on the resistance of the elements connected to the wire, or the battery, for example, the resistors. So a battery is not guaranteed to supply a certain current. The current depends on what's connected to it, okay? If you have a high resistance connected to the battery, it will supply less current than a low resistance load connected to the battery. So in other words, I depends on what's connected to the battery. Delta V is a property of the battery itself. Now, you can go through and we can show that for the power consumed by any resistor or device connected to the source also obeys a similar equation, only I is the current going through that element, and delta V is the potential difference across the element. Okay, so in summary, this equation right here, P is I delta V, applies to any component in a circuit: resistors, batteries, diodes, anything. You measure the current through it, you measure the potential difference across its terminals, and you get the power generated or consumed by that element. So this equation always works. Should be definitely on your cheat sheet for the exam. Okay. Now for resistors only and other elements that obey Ohm's law, we can write this equation, P as I delta V, in a couple different forms that may be easier in some cases to use. Okay, although P is equal to I delta V always works. Okay, so we're going to denote this power consumed or dissipated by a resistor as heat. We're going to denote this by PR, where R is the subscript for resistor. And we can write this as P is equal to I times delta V R. Okay. Now we can use Ohm's law. We can plug in Ohm's law for delta V is equal to IR, and you get I times IR, and you get another expression for the power dissipated by the resistor. It depends on the square of the current times its resistance. Okay. Then you can also, suppose you want to write it in a different way, you start off again with P is equal to I delta V, and we can use we can substitute for I, we can write I using Ohm's law as delta V over R, and then you get that the power dissipated is delta V across the resistor squared over R. Okay, so now for resistors only, we have three different expressions that we can use to calculate the power. So you say, well, why do we want to do this? Well, because there in certain applications we may know two of these three, but not the third one, which we could calculate. But it may be easier if we know two of the three to use one of these particular equations. For example, if we know I and we know R, but we don't know the voltage across it, we can use P as I squared R. If we know the voltage difference, the potential difference, and we know R, but we don't know I, we can use this form. Okay. And then this first form always works. So depending on the problem, it may be more convenient to use one of these forms than another. Okay, there's nothing any better. This first form, remember, always works for every component. Okay, these latter two forms only work for resistors, wires, and elements that obey Ohm's law. Okay. So let's do an exercise, class exercise here. So you and your parents are arguing over whether your light bulb uses more power when you first turn it on or after it's been on for a while. In other words, does a bulb consume more power when you first turn it on or after it's been on a while and the tungsten filament has heated up? Okay, so what we're going to assume here is that your bulb is connected, you plug it into the wall, so the voltage doesn't change. The voltage across the bulb is always equal to 120 volts, the voltage coming out of your receptacles, your wall receptacles. So that doesn't change. So the question is, does the power increase, decrease, or stay the same as it heats up? Okay, delta V is constant. What happens to the current? Because that's going to dictate the power. Okay, so when you first turn the bulb on, it's cold. Okay, and the resistance of the bulb is less. Okay, resistance is less, current is more. Right, so when you first turn on the bulb, lower resistance, higher current, higher power. As the bulb is on longer, the tungsten element gets hot, its resistance to current increases, which means current drops as the bulb warms up. Okay, current drops, power used drops. So the answer to the question is that the hotter bulb has the same voltage drop but lower current, and so it consumes less power. And so your bulb consumes the most power when you first turn it on because it's cold. So this is an example that's really important in home wiring, is that this voltage, if you plug it into the wall, that voltage is fixed unless you load down the circuit. So it's always going to be 120 volts, and then power of your devices, your hair dryer, whatever, your cell phone charger, the power is dictated almost solely by the current. Okay. So let's do another quick calculation. Suppose you have a 100-watt light bulb and the light bulb is plugged in to your 120-volt wall outlet. What's the current through the bulb? Okay, well, we plug in P as I times delta V, and we know delta V is 120 volts, and we know your bulb is 100 watts, and so you get 0.83 amps. Okay, so your light bulb consumes about 0.83 amps. Okay, and these calculations are important because you will, in your home, we'll get into this a little bit later, you have several of your circuits connected in parallel. So, for example, your kitchen and your living room wiring might be in parallel. You might, or the kitchen and the hall. And all of these are in parallel. And if the sum of the currents of everything plugged into those circuits adds up to be greater than about 15 to 20 amps, it'll trip your breaker and your breaker will go off. So that's why sometimes if you have the microwave running and the stove on and the fans on and maybe one or two other things, your breaker will trip and everything will turn off, okay? Because the currents are adding up to more than what the breaker is rated for. It's rated to trip at 15 to 20 amps. So it's important to be able to do these quick calculations relating current, power, and voltage. Okay, so if you have a 400 watt something hooked up at 120 volts, you should know that's consuming 3 amps. Okay, so you should be able to figure out how to keep your current under what the breaker is going to trip. So that's why these calculations are practically important. Now, one other thing here that's an aside, the incandescent light bulb, which runs the current through a tungsten wire, this generates light and a lot of heat, okay? Mostly heat. If you've ever changed the light bulb, it gets hot, right? So incandescent bulbs are not as efficient compared to LEDs and fluorescents. So for these bulbs, the relationship between I and delta V is not quite linear. So if you're doing light bulb calculations and you try to apply the other two forms of Ohm's law, these later two, they don't really work as well because the light bulb does not follow a linear relationship between the current and delta V, and that's necessary to use Ohm's law. So for light bulbs, we really need to use this first form. A couple of years ago in the general physics lab, they were doing a lab with light bulbs, and they were trying to do these little bulbs, and they were trying to use Ohm's law, and people were freaking out because their graphs weren't linear. Well, they're not because the bulb isn't linear. So then I think they changed it now, I think. So anyway, enough of that. Let's do another exercise. So we have 5 different resistors, and they each have a different potential difference across them, and they each have a different resistance. And so the question is, rank them in order from largest to smallest as to the power that is dissipated in each resistor. Okay. So we can use any of our 3 forms to calculate power. So we go back here. We can use P as I delta V, always works. P equals I squared R, works for resistors. P equals delta V squared over R. Now in this case, this third form is the easiest one to use because we already know delta V and we know R right off the bat. So this one, we can use all of them by using Ohm's law on this, but let's just use this third one because we already have delta V and R in hand. So we plug that in, and you get PA as delta V squared over R. Okay. For resistor B, the potential is now 2 delta V, same resistance R. We square this and we get 4 delta V squared over R, and that's 4 times PA. Okay. For wire C, it has a potential difference delta V, but it has a bigger resistance 2R, and we plug that in, and the power dissipated is 1/2 of A. Okay, and the reason is same voltage between A and C. C has twice the resistance, so C has half the current, and therefore C has half the power. Now we go on to D. D has the same voltage difference as A, but only half the resistance, and so you plug that in, and D consumes twice as much power as A. So half the resistance, same voltage, twice the power because you have twice the current. And so the ranking of these is B consumes the most power, followed by D, followed by A, and followed by C. So this is a nice little multiple choice type question for a quiz and an exam, because it illustrates the influences of the potential difference in resistance on power. All right, so you're looking at your utility bill and it's telling you owe $200 for this month, and you're like, there's no way I could have used $200 worth of energy. I think they're trying to screw me. Okay, well, this is where you need to be able to calculate energy and verify that your bill is correct. Okay, so the utility company has a meter, and what they're measuring is energy. Okay, and what they bill you is in units of kilowatt hours, or you may see it as kWh, kilowatt times hour. That's kind of a weird unit, right? It definitely has units of energy because kilowatts is energy per time, hour is time, so it has units of energy, but it's a little strange relative to joules, right? We're used to watts times seconds, which is a joule. So let's do a calculation just to get used to this, and I'm going to give you another homework problem. So your parents are always yelling at you, or you're always yelling at your roommate to turn off the lights when they leave. Okay, and suppose that you go on vacation for a month and you accidentally left on your 100-watt light bulb. Okay, you still have incandescence. Should have switched to LEDs, but you still have an incandescent bulb on, and you leave it on all the time for a month. Okay, let's say 30 days. And the bulb is 100 watts. And so the question is, how much is the utility company going to bill you? So the first thing you have to calculate, if you know the power and you know the time, you can calculate the energy, right? Power times time. And we need to put that in kilowatt hours. Okay, that's the first step. Then the second step is, okay, how much are they billing us for every kilowatt hour? So let's assume that your utility company is billing you 10 cents per kilowatt hour. Okay, so the first thing we need to do is we need to take 100 watts and we need to convert it to kilowatts. Okay, and that's easy. 100 watts is 0.1 kilowatts. The next thing we need to do is we need to convert 30 days to hours. So 30 days, 24 hours in a day, 720 hours. Then the energy usage in units of kilowatt hours is 0.1 kilowatts times 720 hours is 72 kilowatt hours. Okay, so if you know how many watts your light bulb or whatever you leave plugged in and is running, if you know how many watts that's rated for, and usually they'll tell you that it'll be on the tag or something, or in the bulb, it's on the bulb. The next thing we need to do is multiply 72 kilowatt hours by 10 cents per kilowatt hour, and that's a cost of $7.20 per month. Okay, so in this particular case, which is pretty close to what most, I mean, I don't know exactly what they are now, but traditionally it's been around a dime per kilowatt hour. It's about $7 a month to leave your 100-watt light bulb on all the time. So try these, I mean, for fun. Go home and check these out on different things in your house, and you can see what contributes most to your electric bill. If you own a home, it's obviously heating and cooling, as you'll see if you calculate. But So in this case, $7 a month for leaving your light bulb on. Okay, probably should turn it off. Okay. So let's go through current. We already did current and voltage calculations, and we're going to do power calculations now for a circuit containing a single resistor. Okay, then we'll get to more complicated cases with a couple. So let's just do one. Okay, so suppose that the power supply, you have 10-volt power supply, so the potential difference is 10 volts, and that's connected in series to a resistor whose value is 1 kilo ohm. Okay, so what we want to calculate is the potential, is the voltage drop, how much voltage is lost and going across the resistor is dropped. What's the voltage drop across the resistor? What's the current supplied by the circuit to the circuit by the power supply? Okay. Now if I know the power supply's current and its voltage, I can calculate power, right? P is I delta V. And once I know the current and the voltage across the resistor, I can calculate the power consumed by the resistor. Okay. So what's the voltage across the resistor? Well, if it's connected to a 10-volt power supply and there's nothing else in the circuit, it's going to be 10 volts across the resistor, right? Kirchhoff's loop law. You gain 10 volts if we go clockwise and going across the battery. We must lose 10 volts and going across the resistor so that we end up back where we started at 0 volts. Okay, so the potential difference across the resistor is 10 volts. If we know the voltage across the resistor and we know that it's 1 kilo ohm, then the current is 0.01 amps, which is 10 milliamps. Okay, so now we know the current dissipated by, or the current going through the resistor. Now, important point here, there's only one path for the current to flow, right? This is a single loop, there's no junctions, which means that there must be 10 milliamps flowing through the battery as well. So it must be 10 milliamps everywhere in the circuit. Okay. Now, if we know that the power supply gives you 10 volts of voltage and it supplies 10 milliamps of current, then the power supplied is 100 milliwatts. Okay. And you can calculate here, I did it in 3 different ways just to show you get the obvious that you get the same result in all of them. So we can calculate P as I times delta V across the resistor, and you get 100 milliwatts. If you choose to use the voltage square divided by R, you get 100 milliwatts. And if we choose the current squared times the resistance, you get 100 milliwatts. And so it illustrates the obvious that you can use any of these 3 methods for the resistor, these equations, and you get the same thing. Okay. So this also illustrates one other point here. The current supplied by the battery, again, depends on what's connected to it. Okay. So for example, instead of 100 ohms, if I connect, or 1,000 ohms, if the resistance was 100 ohms, then the current would be 10 volts over 100 ohms, which would be 0.1 amp, which is 100 milliamps. And if we plug that in, 100 milliamps instead of 10, you would get 1 watt instead of a milliwatt. So in other words, the current and the power supplied by a battery depend on what's connected to it. Okay, the voltage is a property of the battery, and that's important. Okay, because the current depends on the battery's capability, but also on the circuit, on what's connected to it. So you might ask, okay, if most circuits only have more than one resistor, you know, obviously they do. Most circuits have many resistors and other elements connected. Why are we wasting our time trying to really understand a single resistor circuit? And the answer is that most real circuits are much more complicated than a single resistor, okay? True. But any circuit can be broken down into sections, each of which is either series or parallel. And for each of these sections, we can model the circuit as a circuit containing a single resistor, okay? Just like we did the equivalent capacitance for multiple capacitors in series and parallel, we can do the same thing with resistors. So for any big, my claim is for any big mess of components, we can model it as a circuit with a single resistor, which makes the calculations much simpler. So let's move on. There's two important classes of circuits, and we've already done these already. We've introduced them. It's called series circuits, where elements are wired in series, and parallel circuits, where elements are wired in parallel. And if we can understand series and parallel, most circuits can be broken down into sections that are combinations of these. So our next step is to really understand the series circuit well, and then to really understand the parallel circuit well. And that will give you the foundation to go on and study further more complicated circuits. So we have to have a good base. We have to have a good foundation. Okay. So let's do series. Series seems easier for students at first when you're wiring them together. I know in lab students have an easier time with series than parallel. So series wiring basically just means that the elements connected together are connected one after the other. Okay, and they're connected to form a single loop. Okay, so here you have your battery, your 9-volt battery, and we connect it to the one end of the first resistor to the positive terminal. We connect the other end to the next resistor. Then on the other end of the resistor, if we had another resistor, we would connect that one up to this resistor, and it's just like a train, right? These are the little cars of the train. They're connected together, okay? And then finally, after the last resistor, we connect it to the negative terminal. And this is what's called a series circuit. These are easy to wire. You just wire one after the other, okay? And the main point about a series circuit, when you wire any elements in series, is that they all must have the same current, because there's only one path for the current to flow, right? So here's the current I. It flows through R1, flows through R2. It can't go anywhere, right? And charge can't build up, so it's the same flow all the way through the wire. Just like a water circuit has the same flow everywhere if it's just a single loop. The water can't build up anywhere. So the series circuit has the same current everywhere. And we're going to use that to calculate the resistance, or the equivalent resistance of wires of resistors in series. Sorry, I'm tired today. So suppose that we have two resistors, R1 and R2, and they're in series. And Kirchhoff's voltage law, the loop law, says that the potential difference, sorry about that, this picture, these are all deltas. The picture that I have doesn't have the deltas. Says that the potential difference gained across the battery, if we're going clockwise, must be the sum of the potential differences lost in going across these two resistors. So in other words, they all have to add up to be zero. Positive number, two negative numbers, they all have to add up to be zero. And that's the same as saying that the voltage gained in going across the battery is the sum of the voltages lost in going across the resistors. Okay. Now we can write the potential difference across resistor 1 is IR1, and the potential difference across resistor 2 is IR2. Current is the same through both, so we can factor this, and is equal to I times R1 plus R2. So in other words, these two resistors behave when you combine them in series, behave the same as if I just had a single resistor of value R1 plus R2 in the circuit. So we can model these series resistors as a circuit with a single resistance, R1 plus R2. And we can go on and we could expand this to any number of resistors in series. The equivalent resistance, some authors use R series, some use R equivalent, some use R total, call it what you will. It's the equivalent resistance of resistors in series is the sum of all the resistance values. And so we can model our circuit as a single resistance of value R equivalent, and we can apply all of our techniques to get the circuit properties using this simple circuit. So why do we do this? Usually we do this because the first thing you're going to want to get in the circuit, remember we want to get the voltage drops across the resistors and everything. The first thing we need to do to get that is we have to find the current. And so calculating the total resistance, this equivalent resistance, we can divide the battery voltage, delta V battery, by the total resistance, and that gives us the current. Okay? So that's why it's easiest to get the equivalent resistance is to get the current. Okay, this circuit, it's pretty simple. There's no need to do it here. But once you get the current and you know the resistance of each one, you can get the voltage drops across each. Once we know the current and the voltage drops, we can get the powers, and then we're done. So it's often easier with complicated circuits to get the equivalent resistance. And for series, it's just the sum. So let's do an example here. Suppose you have a 6 ohm resistor and you have a 3 ohm resistor, and they're connected in series with a 12 volt battery. So see that they're in series, they're connected one after the other, and there's a single loop. That's a series circuit. Okay. You should know difference between series and parallel when you're done. Okay. So the first question is, what's the total or equivalent resistance? Okay, well, 6 ohms plus 3 ohms is 9 ohms. So the total, this circuit behaves the same as a single resistor of value 9 ohms. Okay, what's the current? Well, to calculate the current, it's the battery voltage, delta V battery, divided by the total resistance, which is 9 ohms, 1.33 amps. Okay. Once we know the current, it's the same in both. We can multiply by the resistance, and we can get the voltage drops across both. 8 volts is dropped by the 6 ohm resistor. 4 volts is dropped by the 3 ohm resistor. And so now we get the potential differences. Now on homeworks and especially on exams, here's where you need to check your answers, okay? And you should know right after if you check whether your answer is right or wrong. So let's check. We're losing 8 volts across the 6 ohm resistor. We're losing 4 ohms across the 3 ohm resistor. The sum of the voltage drops is 8 volts plus 4 volts is 12 volts. That must equal what's gained by the power in going across the power supply. Okay, 12 volts must equal 8 plus 4. In other words, the sum of the voltage drops must be 0. So good, all right, we have some confidence that our answer is right because the answer is consistent with the loop law. So this is always a good first check, okay? Now in part C, let's calculate the power consumed by each resistor, okay? I chose to use I squared R, but you could use delta V squared over R, or you could use I times delta V. You can use any of them. I just chose to use I squared R. So I plug that in. I is 1.33 amps, 6 ohms, 10.6 watts is consumed by this resistor. 5.31 watts consumed by the 3 ohm. How can I check my calculation? Well, I can check the total power consumed, in this case is 15.9 volts. Okay, what's the power supplied? Well, it's 12 volts times 1.33 amps, 16, okay, with slight rounding error. So the power consumed by the devices must add up to the power supplied by the source. So another check on our answer. So there's multiple ways that you can check, multiple paths for checking your answers that I encourage you to start doing now and on the exam, so you can check to make sure that you didn't make an algebra mistake. Now, one important point here, and then I think we're going to end it for today, is if you look at the series circuit, this 6 ohm has twice the resistance as the 3 ohm. Okay? If they both have the same current, and this one has twice the resistance, it will have twice the voltage, because Ohm's law says that delta V is IR. They both have the same I. Bigger R means bigger delta V. So in this case, twice the resistance, twice the voltage drop. Okay? What does that mean in terms of power? Well, if they have the same current, bigger resistor has a bigger voltage drop, it will dissipate more power. And so the 6 ohm resistor consumes twice as much power as the 3 ohm resistor, because they both have the same current, but this one has twice the voltage. So larger resistors in series consume more power than the smaller resistors. The other thing too is if you keep wiring more resistors in series, what do you think is going to happen to the current? Okay, well, let's look. Remember, the equivalent resistance is just the sum of the resistances. So the more things we hook up in series, the bigger the equivalent resistance. Bigger resistance, less current, same total voltage. The power consumed by the circuit decreases. So the more things you hook up in series, the more your total resistance becomes, the less your current supplied by the battery becomes, the less power that your battery supplies to the circuit. Your battery will last longer. Okay. So I encourage you, I put another example or two on series circuits in the back of these notes. I encourage you to work on those, and we can go over those Monday in lecture. We're going to start tomorrow with parallel wiring, then we're going to get into short circuits, and then we're going to move on the next day, Monday, with a couple other topics like RC circuits and voltmeters and ohm meters. So have a good day.